Welcome to Modern SQL for Data Analysts. This is not just another SQL course. Most SQL tutorials stop at syntax and toy examples. This course is different. It is sharp, hands-on, and built for the way SQL is actually used in the modern data world. We will be using Google BigQuery and real e-commerce data, and we will also connect everything to the way analysts now work with AI-powered tools like ChatGPT, Copilot, and Gemini. Instead of just memorizing commands, you will learn how to think in SQL. That means you can understand the logic behind queries, you can sanity check AI-generated SQL, and you can deliver insights faster because you know what good SQL looks like. Now let me walk you through how this course is structured. We start with Section 1, Introduction and Setup. Here you will get the course orientation, understand why SQL is still essential in the age of AI, and set up BigQuery so you can follow along with all examples. Section 2 is the foundation level. This is where you build your SQL base. You will learn how to explore tables in BigQuery, write basic queries, filter data, and use the essential commands. We will practice selecting columns, using from, filtering with where, and aggregating results. Each concept will be reinforced with hands-on exercises, so you do not just watch, but actually write queries yourself. Section 3 is the intermediate level. Here we step up into the skills every analyst needs on the job. You will learn how to join tables, handle duplicates and null values, apply data quality checks, and write conditional logic with case statements. You will also practice writing subqueries and common table expressions, so your code is cleaner and easier to maintain. This section is where you stop feeling like a beginner and start writing SQL that works in production. Section 4 is the master level. In this section, you will learn advanced techniques like window functions, performance tuning, and modular query design. You will see how to structure queries for scalability and how to test and optimize them. Most importantly, this is where we bring AI into the workflow. You will learn how to use tools like ChatGPT and Copilot to accelerate your work, how to review and correct their output, and how to combine human reasoning with AI assistance. By the end of this section, you will be working at a professional level. So that is the journey, from setup to foundation to intermediate to mastery. Each step designed to build on the last and give you real job-ready skills. People ask the same question again and again. Is it still worth learning SQL in the age of AI? With tools like ChatGPT, Copilot, and Gemini, it feels like the machine can write queries for you. So why bother learning? The reality is that AI will not remove the need for SQL. It will only raise the bar for what good analysts can do with it. Here's the truth. SQL is not going away. Every database, every warehouse, every pipeline in modern companies still runs on SQL. The reason is simple. SQL is the universal language of data. It is the bridge between raw information and business decisions. What AI does is make bad SQL look convincing. It can generate queries instantly. But without human understanding, those queries often contain errors, wrong joins, missing filters, or assumptions that do not fit the business context. If you cannot read and reason through the logic, you cannot trust what AI gives you. That is where your skill comes in. Analysts who understand SQL will use AI as an accelerator. Instead of writing every query from scratch, you can guide AI with better prompts. You can spot mistakes instantly. You can refactor messy outputs into clean, production-ready code. You can orchestrate the process end-to-end instead of just copying and pasting. The real value is not typing faster. The value is understanding how data should be structured, how results should be validated, and how business context changes the query. That is the skill companies pay for. That is why analysts who know SQL will be more valuable than ever. Think about it this way. Two people use the same AI tool. One has no SQL knowledge and just pastes prompts. The other knows SQL deeply and can guide, correct, and optimize what comes back. Which one do you think delivers results that the business can trust? Which one do you think moves faster and adds more value? It is always the second person. So the point is clear. Learning SQL in the AI era is. In this lecture, we are going to get hands-on with Google BigQuery. BigQuery is the cloud data warehouse from Google. It is part of Google Cloud Platform, and it is designed for analytics at scale. With BigQuery, you can run SQL queries on massive datasets in seconds. Companies use it to analyze customer behavior, track operations, and power dashboards with real-time data. For this course, we will be using BigQuery because it is fast, it is reliable, and it lets us work with real datasets without having to manage servers or infrastructure. Everything runs in the cloud. The good news is that you do not need to pay anything to follow along. Google Cloud provides a free tier for BigQuery. You can either create your own free project or use your company project if you already have access. All you need is a Google account to get started. Here is the step-by-step process. First, go to console.cloud.google.com. Sign in with your Google account. Second, create a new project. You can give it any name you want. For example, SQL course or test project. Third, make sure BigQuery is enabled. You can do this by searching for BigQuery in the search bar at the top and clicking on BigQuery. If it is not yet enabled, it will prompt you to enable the API. Once you are in BigQuery, you will see the BigQuery console. This is where you write queries, run them, and explore tables. On the left side, you will see your project name. Under that, you will be able to add datasets and tables. Now, let us connect the dataset we will use throughout this course. Click Add Data on the left. Choose Public Datasets. In the search bar, type The Look. You will see the Look e-commerce dataset published by Google. Click View Dataset. Once it opens, click the star icon so that it is saved to your project for easy access. The Look dataset contains real e-commerce style data, including customers, products, orders, and transactions. It is perfect for practicing SQL in a real-world setting. Now, here is the important step. When you create your Google Cloud project, make sure the location is set to US. The Look dataset is hosted on US servers, and by setting your project location to US from the start, you will be able to query it directly without having to create snapshots or copy tables. That is all you need to get set up. In the next lecture, we will start exploring tables inside BigQuery and write our first queries.
In this short tour, we are going to look at the main parts of the BigQuery interface so you know exactly where everything is before we start writing queries. First, in the center of the screen, we have the code editor. This is where you will type and run your SQL queries. You can open multiple tabs if you want to work on more than one query at the same time, and you will also see buttons at the top to run a query, save it, or share it. This will be the main workspace throughout the course. Now let's move to the left-hand panel. At the top is your project. Inside a project, you can have one or more datasets, and each dataset contains multiple tables. For example, here you can see a dataset with tables for orders, products, and users. This is how BigQuery organizes your data, and it is important to know the hierarchy, project, dataset, then table. When you click on a table, you can explore its structure. You will see a list of fields along with their data types, such as integer, string, or timestamp. This is useful for understanding what kind of information is stored and how you can query it. Knowing the schema before writing queries helps avoid mistakes. Finally, let's look at the tabs across the top of the table view. The most important one is the Preview tab, which lets you quickly see a sample of the rows in the table without writing a query. There are also tabs for details and schema, but Preview is especially handy when you are exploring data for the first time. And that's it. You now know where to write queries, how to navigate your project's datasets and tables, and how to quickly check the details and preview of your data. With this foundation, you are ready to dive in and start working with SQL inside BigQuery.
Today, we're starting with the foundation of SQL, the select and from statements. These two commands are the backbone of almost every query you will ever write. If you understand them clearly, everything else you learn in SQL will make a lot more sense. Let's begin with the concept. The select statement tells the database what columns you want to see in the output. You don't always want the full table. Sometimes you only need one or two specific pieces of information, and select lets you control that. The from statement tells the database which table the information should come from. Think of it like this. Select is what you want, and from is where you want it from. Together, select and from form the simplest possible query. Why does this matter? Imagine you're working in a company database with hundreds of columns and millions of rows. Pulling everything at once would be overwhelming, slow, and often completely unnecessary. By using select and from, you can target exactly the fields you need, making your queries faster and your results cleaner. Now let's talk about use cases. You'll use select and from anytime you want to pull specific columns from a table. For example, if you only want customer names, you don't need addresses, phone numbers, or anything else. Select lets you focus on just the names. This is also the very first step in almost every SQL query. Filtering rows, grouping values, joining multiple tables, all of these operations begin with a select and a from. They are truly the foundation of SQL. There are also some practical tips. When working with AI tools, you'll want to be very explicit about what table and what columns you need. If you just say, "Get me customer data," the AI might guess wrong. Instead, say, "Select the first name and last name from the customers table." That kind of clarity avoids errors. And even if an AI generates your query, you should always validate it before running it, especially when working with large or important datasets. Now let's look at the syntax. A basic query looks like this. You type select, then list the column names, and finally write from with the table name. The order matters. Select always comes before from. If you switch them, the query won't run. All right, let's switch over to BigQuery and see this in action. Here's our first example. We're selecting just the first name and the last name columns. The result will only show those two columns. This is the cleanest way to narrow down what you need. In our second example, instead of picking columns one by one, we select everything using the star symbol. That means we're pulling all columns in the table. This is quick and sometimes useful for exploration. But it's not a best practice when building production queries. It's better to be intentional about what you want. Next, let's look at distinct. If we ask for the country column, normally we might see the same country repeated many times across different rows. By adding distinct, the database removes those duplicates and gives us only the unique list of countries. This is really handy for finding categories, regions, or any field where you only want the distinct values. Another important feature is limit. If we write a query to select 3 or 4 columns, we can add limit 10 at the end. This tells the database to only return 10 rows. Limit is useful for testing or previewing data without loading the entire dataset. It saves time and keeps your results manageable. Finally, let's talk about renaming columns, also known as using aliases. By adding the keyword AS, we can give a column a new name in the results. For example, instead of showing first name, we could display it simply as F name. Aliases are especially useful when you're combining multiple tables and need to avoid confusion, or when you want the results to look cleaner for a report. And that covers the basics of select and from. We've seen how to choose specific columns, how to select all columns, how to remove duplicates, how to limit rows, and how to rename output. These 5 techniques alone already cover a huge percentage of the queries you'll write in real life. The important thing to remember is that every complex SQL command builds on this foundation. Filtering, grouping, joining tables, subqueries, window functions, they all start with select and from. Master this pattern, and you'll be ready for everything else that comes next. In this lesson, we are going to learn how to filter data using the where clause. Filtering is one of the most important parts of SQL because it lets you narrow down large data sets to only the information you actually need. The where clause filters rows in a table based on a condition. In other words, it limits the results so you only see the rows that match your criteria. This helps you avoid scanning through unnecessary data and focus directly on what matters. Let's talk about a few use cases. Filtering is essential anytime you want to get only the rows that match a specific value. For example, you might want to find all customers from a single country. Filtering is also used to exclude unwanted data. If you do not want test accounts or inactive users, you can filter them out. And filtering is what allows you to focus your analysis on just a subset of records instead of working with everything all at once. A practical tip here is to always specify your condition clearly, especially when working with AI tools. If you just say, filter the data, the AI may not know what you mean. Instead, say, filter for customers where the country is equal to Canada. And it is always a good idea to double-check the filter logic so you do not accidentally miss rows or include too many. Now let's move over to some examples in BigQuery. Our first example shows the basic syntax of where. We start by selecting the first name and last name columns, and then we add a where clause to only return rows where the country equals United States. This gives us only the people from that country instead of everyone in the table. Filtering can also use other operators, not just equals. We can use not equal, greater than, less than, greater or equal, and less or equal. These operators allow us to set different conditions depending on the data we are working with. For example, let's look at filtering numbers. If we select the first name, last name, and age columns, we can add a condition that only includes rows where the age is greater than 30. This is a very common use case, finding customers or products that meet a numeric threshold. We can also filter by dates. Suppose we select the first name and the date when the account was created. By adding a where condition for created at greater or equal to the 1st of January 2023, we only return users who signed up this year or later. This is incredibly useful for time-based analysis. Next, let's look at combined filtering. We can add more than one condition by using AND and OR. For example, we can return users where the country is the United States and the age is less than 25, or where the country is Canada. This type of combined logic helps us capture very specific groups of records. Finally, we can filter by multiple values using the IN keyword. Instead of writing several OR conditions, we can say country in and then list several options, like United States, Canada, and Mexico. This tells the database to return any rows that match one of those listed values. And that is the foundation of filtering with the where clause. We have seen how to filter for specific values, how to use operators like greater than or less than, how to filter dates, how to combine multiple conditions, and how to filter by multiple values with IN. These techniques make your queries much more powerful. Instead of pulling everything, you can now focus your analysis on exactly the slice of data that matters most.
In this lesson, we are going to look at how SQL can summarize data using aggregate functions. Instead of returning every single row, aggregate functions calculate a single value based on multiple rows. This makes it easy to quickly answer questions like, what is the smallest value, what is the largest value, or what is the average value in a column. The most common aggregate functions are min, max, and avg. Min finds the lowest value in a column. Max finds the highest value. AVG calculates the average across all the rows. Together, these functions are used constantly in reporting and analysis. Let's think about some use cases. Suppose you are analyzing sales. You might want to find the lowest and highest order sizes in your data. You might also want to know the average number of items customers buy. With a single aggregate query, you can answer these questions without having to scan through the full data set. Another use case is quality control. You can find the minimum and maximum delivery times to see whether there are outliers. Or you can calculate the average and standard deviation of a metric to measure consistency. Now let's walk through an example. Here we are selecting 4 different aggregates from the number of items column. The first function, min, gives us the smallest value in that column. This tells us the fewest number of items that appeared in a single order. The second function, max, gives us the largest number of items. This tells us the maximum order size in the dataset. Next, we use AVG. Instead of returning a long list of numbers, AVG condenses them into one value, the mean number of items per order. To make the result cleaner, we wrap it in a rounding function so the average shows with just 2 decimal places. Finally, we calculate the standard deviation of the same column. Standard deviation measures how spread out the values are. A low standard deviation means most orders are close to the average size. A high standard deviation means order sizes vary a lot. This is extremely useful for understanding consistency in your data. And just like the average, we round the standard deviation to 2 decimal places to keep it easy to read. What makes aggregate functions so powerful is how quickly they turn raw data into insights. Instead of returning hundreds of rows, they can give you a single number that summarizes the entire column. With just one query, you can answer big questions like, what is the range, what is the average, and how much variation exists. The important thing to remember is that when you use aggregates like min, max, and AVG, you are condensing multiple rows into a single result. You are not listing out every order or every customer, you are summarizing them. And that is the foundation of working with aggregate functions. You have seen how to calculate the minimum, the maximum, the average, and the standard deviation. These 4 metrics alone can give you quick insight into almost any numeric column. In the next lessons, we will build on this by combining aggregates with grouping to break results down by category or by segment.
In this lesson, we are going to look at how SQL can group rows together using the group by clause. So far, we have learned how to summarize an entire column using aggregate functions like min, max, AVG, and standard deviation. But sometimes you do not want just one number for the entire table. Instead, you want those numbers broken down by category, by region, or by some other column. That is where group by comes in. The group by clause tells SQL to gather rows that share the same value in a column and then apply an aggregate function to each group. This way you get one result per group rather than one result for the entire dataset. Let's talk about some use cases. Group by is essential when you want to calculate averages or totals per category. For example, you might want the average price per product category, or the total sales per region. Group by also helps summarize large datasets by key fields like country, department, or customer type. And it is the foundation for comparing metrics across different groups, like seeing which brand has the highest average price. Now here is an important tip. When you use group by, every column in your select statement must either be included in the group by or be wrapped in an aggregate function. This is one of the most common mistakes beginners make. If you forget to add the column to group by, the query will not run. Let's look at an example. In this query, we are selecting the category column, the brand column, and then calculating the average price. Without group by, SQL would not know how to match categories and brands with averages. But when we add group by category and brand, SQL creates a result for each unique pair. So if you have 5 brands inside one category, you will get 5 rows, each with the average price for that brand. This makes it very easy to see comparisons. You can instantly find which categories tend to have higher or lower averages, and then drill down into specific brands. There is also an alternative way to write group by when you want to group by all non-aggregated columns in your select. Instead of listing them one by one, you can write group by all. This tells SQL to automatically group by any column that is not inside an aggregate function. In our example, since we selected category and brand along with the average price, group by all would create the same result without needing to list category and brand separately. Keep in mind that not every SQL engine supports group by all. It is available in some systems like BigQuery, but the safer, more portable method is to explicitly list the columns. Still, it can be a useful shortcut when you are grouping by many fields. And that is the foundation of group by all. With this clause, you can turn large datasets into compact summaries that are grouped by categories or regions. Combined with aggregate functions, group by is one of the most powerful tools for analysis in SQL. By mastering group by, you can answer real business questions like which category sells the most, which brand has the highest average price, or how performance differs across regions. This is the step that turns SQL from just pulling raw data into creating meaningful insights. In this lesson, we are going to learn about creating custom columns in SQL. The concept is simple. You can create new columns in your query by combining or transforming existing ones. This helps format the data in exactly the way you need, without changing the original table. The underlying source remains the same, but the results display with your custom logic applied. A very common use case is combining multiple columns into a single column, for example, joining a first name and a last name into one full name field. Another use case is creating formatted strings for display, such as adding text or symbols around numeric values. You can also derive completely new values by performing calculations on existing columns, which is very useful when you want to add insight without altering the raw source tables. A couple of important AI tips are to always be clear in your prompt about how you want the custom column created. If you want to join 2 names, specify that explicitly, and if you want to calculate a new value, explain the formula. Finally, double-check that the alias you use matches the intended column name because the alias is what will show up in the results, so it should be descriptive and accurate. That is the core of creating custom columns in SQL. By combining, formatting, or calculating values on the fly, you can make your query results easier to read and directly aligned with your analysis needs, all without changing the underlying data. In this lesson, we are going to explore one of the most important concepts in SQL, the join. Joins let you bring together rows from two or more tables based on a related column, and this is what makes relational databases powerful, because it means you can combine information that is spread across different tables. The basic idea is that you tell SQL which two tables you want to connect, and which column the connection should be made on. For example, you might have an orders table and a customers table. Orders include a customer ID, and customers include that same ID. By joining the two tables on the customer ID, you can see order details alongside customer details. There are many use cases for joins. You can match related records across tables using a shared key. You can enrich a dataset by pulling in columns from another table, and you can build richer analysis by linking multiple sources together. The key is always to be clear about which tables you are joining, and to make sure the join condition makes sense for your business logic. Now let's talk about the different types of joins. The first one is the inner join. An inner join returns only the rows where there is a match in both tables. Think of it like a Venn diagram, where you only see the overlapping area. This is the most commonly used join, because it ensures that you are only looking at records that exist in both places. The second type is the left join. A left join returns all the rows from the left table and then matches from the right table. When possible, if there is no match, you will see null values on the right side. This is useful when you want to make sure you keep everything from your main table but still add extra information when available. The opposite of that is the right join. A right join keeps everything from the right table and adds matches from the left. When possible, this is less commonly used, but it can be helpful in situations where the right table is your main source and you want to preserve all of its rows. Finally, we have the full outer join. This one returns all rows from both tables. Where there is a match, the rows line up. Where there is no match, you still get the row, but with null values filling in the gaps. This is the most inclusive type of join, and it is useful when you want to see both the matches and the non-matches across two tables. If you are a visual learner, the diagrams on this slide show exactly how each join works. And if you are a meme learner, you might notice that each join type has its own face. Personally, the inner join one sticks with me the most. It looks serious, like it is only here for exact matches and nothing extra. Meanwhile, the full outer join looks like it is just trying to include everyone, even if they don't quite belong. The important takeaway is that joins are not one size fits all. You choose the type of join depending on what question you are trying to answer and which table you want to preserve in the results, and once you understand the difference between inner, left, right, and full outer joins, you will have the tools to combine data in flexible and meaningful ways. When working with SQL, it is not enough to just know the syntax. You also need to make sure that the data you are working with is clean. One of the biggest issues you can run into is duplicates. If you try to join tables that contain duplicates on a key column, the results can explode. Instead of clean matches, you will see repeated rows, inflated counts, or totals that do not make sense. That is why checking for duplicates is such an important part of data quality control before running your queries. So what do we mean by a duplicate? A duplicate happens when the same value or the same combination of values appears more than once when it should really be unique. For example, a product ID should only exist once for each product. If you see that same product ID show up multiple times, something is wrong. This could be a data entry mistake, an error in the upstream pipeline, or just a missing constraint in the database. Whatever the cause, if you do not catch it before joining tables, your results will be unreliable. The way we check for duplicates in SQL is straightforward. We group the data by the column that should be unique, and then we count how many times each value appears. If everything is clean, each value should only show up once. If something appears more than once, you have found your duplicates. To make it even easier to spot issues, we can order the results by the count in descending order, so that the worst offenders appear right at the top. This type of check is not about producing a final report. It is about making sure the foundation is solid before building analysis on top of it. You do not want to discover halfway through that your totals are doubled because a join was performed on a non-unique column. A quick duplicate check can save hours of debugging later. And here is where AI tools can help. You can simply tell an AI assistant check if product_ID appears more than once, or show me a count of each value in this column sorted from highest to lowest. That kind of instruction will usually give you the exact SQL you need. The key is to be clear about which column should be unique and to ask for the count grouped by that column. So to summarize, duplicates matter because they break your joins, inflate your results, and create misleading insights. By grouping and counting, and by ordering the results to spot problems quickly, you can control for duplicates as part of your workflow. This step may feel small, but it is a cornerstone of data quality control, and it ensures that the queries you write afterwards will actually return the truth instead of noise. After checking for duplicates, the next major data quality issue we need to watch out for is null values. A null is not zero, not an empty string. It literally means missing or unknown. And missing values can break your queries in subtle ways. If you try to join tables on a column that contains nulls, those rows will never match, which means you silently lose data. Nulls can also cause problems in filters, in aggregations, or in conditions. And to make things trickier, functions like count will ignore nulls unless you specifically tell it to include them. That is why before running joins or calculations, you should always check whether critical columns contain nulls. The way to check for them is simple. Use a where clause with is null to return all rows that are missing a value in that column, or use count with is null to see how many records are affected. If the number is small, you might decide to drop those rows, but if it is large, you know the problem has to be addressed upstream. This step is not about making the data perfect on your own. It is about being aware of where gaps exist so you do not build analysis on missing foundations. And just like with duplicates, AI tools can help here if you communicate clearly. You might say find all rows where product ID is null, or count how many records are missing values in this column. You can also tell AI whether you want to ignore nulls or include them in an aggregation. And if nulls appear in join keys, you should explicitly ask AI to exclude those rows. This way you make sure your joins are reliable and your counts reflect the reality of the data. So to summarize, duplicates inflate your results while nulls silently erase them. Both are dangerous if left unchecked. And by building quick checks into your workflow, you ensure that the queries you write will return trustworthy insights instead of misleading numbers. In SQL, sometimes you need more than just pulling data directly from a column. You need to add logic, and that is where the case statement comes in. Case lets you build conditional logic inside your query, almost like an if-else statement in programming. It evaluates conditions in order and returns a result based on the first condition that matches. This means you can categorize, group, or label your data on the fly without changing the underlying table. There are a few classic use cases. You can categorize numeric values into ranges, for example, turning a sale price into categories like high, medium, or low. You can create flags, for example, labeling whether a customer is active or inactive based on the last purchase date. Or you can apply business logic, like checking if a quantity is above a threshold to label it as bulk. The syntax is straightforward. You start with case, then add when, followed by a condition, and then followed by the result you want to return. You can have multiple when clauses in one case, and finally you close it with else for all rows that did not match any condition, and end to finish the block. A key detail is that SQL executes the conditions in order, and it stops as soon as one condition matches, so if you have overlapping ranges, the first one that matches will take precedence. This is why it is important to put the conditions in the right sequence, otherwise you might get unexpected results. The else part is optional but strongly recommended, because if no condition matches and there is no else, SQL will return null. That might be fine in some cases, but often you want to be explicit, maybe returning a default label like other or unknown. Another tip is that case works not just in the select list but also inside order by and group by, which makes it very flexible. For example, you can sort rows into a custom order defined by your own logic instead of relying on the default column order. Now, just like with other concepts, AI tools can generate case statements for you, but you need to be clear. Tell the AI what the input column is, what the conditions are, and what you want returned for each condition. For example, say categorize sale price into high when it is above 100, medium when it is between 50 and 100, and low otherwise. That phrasing will give you the exact case statement you need. Also double-check that the order of conditions matches your intent, because the